Hello. Hello. In the previous class, we were discussing infinite deep square potential well. In today's class also, we are going to see some important problems, uh, or you can say some important concepts that we were discussing in the last session also, and we are going to continue the discussion on these some of the very important concepts with regards to infinite deep potential well. Okay. So without wasting time, let us start. So the last problem we were discussing was somewhere related to uh, infinite deep potential well. And today also we are going to continue with the same. We've already had a discussion over a problem where we wrote our initial wave function psi x as ax capital A small x times A minus x. And then we tried to write it in the linear combination of the various eigenkets. And we realized from the symmetry of the wave function that this holds a very similar symmetry as that of the ground state of the infinite deep square well. And therefore, we also dig deep into this problem and uh, understood uh, how significant contribution C1 mod square was giving. And if you remember, the contribution from C1 mod whole square was around 99%, almost 99.9% of the contribution was coming from C1 mod whole square, and which was much anticipated. And also we tried to find the average value of energy uh, where the initial wave function was given in this manner, and the particle was supposedly in a infinite deep potential well. So the average value of energy was slightly greater than the ground state energy, which was also much anticipated. Because, all this entire psi x is not only the ground state, rather it also contains the other states, that is the other odd states. So therefore, all these odd states are also going to give some contribution to the average value of the energy. So therefore, you will not get the exact ground state energy. But one thing that stands out and which you should really take care of is the understanding that uh, of the symmetry. See, the symmetry of the wave function was such that we were trying to speculate, and whatever speculation we thought were exactly in line, and we actually calculated all these things. Later on, we also thought that if some phase factor is multiplied, or some relative phase factor is multiplied with a particular um, coefficient, that is, let's say in this manner, I'm saying, if your psi x is written as a linear combination of two eigenkets, and one of the coefficient of one of the eigenket is multiplied with the relative phase constant, then how psi x comma t would change, how psi x comma t mod whole square, which is the probability density, changes. And we actually found that it only shifts the initial time t equal to 0 measurement, that at initial time t equal to 0, psi mod whole square would start uh, from from psi mod whole square would start differently with different phi's. So basically, we tried to see how things would reflect in the average value of the position. So average value of position turned out to be a by 2 uh, at time t equal to 0 if the initial phase phi was taken to be equals to pi by 2. And if initial phase phi was taken to be equals to pi, then the average value of the position, or you can say the expectation value of the position, uh, turned out to be greater than a by 2. So it is just like it is switching the initial conditions. This particular phi it switches the initial condition. So relatively, if I multiply a phase constant uh, to a particular coefficient of an eigenket, then things may vary. But if your wave function is a particular eigenfunction only, And if you multiply it with phase constant e raised to power minus iota E1 t upon h cat, then things won't matter. But if you multiply a particular one, like here, uh, then obviously things would change. So this is what I wanted to lay stress on. Now, another thing that I wanted to lay stress on was this particular fact. Let's say I would start with the concept uh, by assuming. So let us assume that that an deep infinite deep square well problem. Let us assume an infinite, sorry, deep square well problem with with wave function, with the wave function of the particle expressed as. So what I'm expressing the initial wave function of the particle psi x, and let's say it is given by ax, where x lies between 0 and a by 2, and it is equals to a times small a minus x, and where x is given by a by 2 to a. So let's say if I make the plot of it, so how would the plot look like? So I know that my wave function initially varies linearly, and then also again it varies linearly, although but the slope is negative, and it will attain 0 at x equal to a. So at exactly x equal to a by 2, it will attain a peak, because if I place a by 2 here, then it will be a by 2, and here also a by 2. So clearly your wave functions, I'll write it here, a by 2, and this a, and here it is 0. Now, as you see that, as you can clearly, I will write it here itself so that you are not, you will be able to get what I want to suggest. So the point I want to make is, clearly you can see, clearly one can observe that wave function psi x is continuous, even at x equal to a by 2. Okay, even at x equal to a by 2. That is evident. You can find the limit as x tends to a by 2. So both left hand and the right hand limits are same. However, it is discontinuous at a by 2. So how non-differentiable. However, psi x is non-differentiable at a by 2. So because there is a sharp edge also, you can see. Otherwise, also, if you want to find the derivative here would come out as simply a, and here it will come out as simply minus of a. So derivative to the left of a by 2 is minus of a, and derivative to the right of a by 2 is plus of a. So clearly psi x is non-differentiable at x equal to a by 2. Okay. Okay. And we have also seen this particular fact that the continuity of uh, the, the derivative. Okay. So, so continuity of the derivative as such is not required. And in fact, we have seen in our first lecture itself that even in the infinitely deep square well, the derivatives were discontinuous. If you remember, here the wave function psi x can be written as some root over 2 and some sine n pi x upon a. If I just want to write my uh, wave function that is a ground state, it will be root 2 by sine pi x upon a. And here I know that wave function psi x was equals to 0. Now if I differentiate here, it will come out as 0. And if I differentiate this, even at x equal to 0, it will be root over 2 upon a pi upon a, and cos pi x upon a, and at x equal to 0, cos 0, at x equal to 0, cos 0 is 1. So clearly, at x equal to 0, psi dash x is discontinuous. Okay, so if you want to see that at 0 minus, the derivative of the wave function is 0, and to the right of 0, the derivative of wave function is root 2 by pi upon a. So clearly, continuity of derivative as such is not required, but a few things one needs to really take care of, that I really want to emphasize in this particular problem itself. From this problem itself, I'm going to emphasize a little bit of important concept that is you really need to pay attention. Okay, so continuity of derivative as such is not required, and however, you can see that here clearly, this particular sharp edge. So here you can clearly see that your psi dash x is discontinuous. Again, I'm emphasizing that psi dash x on the left hand side would be simply a, and psi dash on the right hand side of a by 2 would be simply minus of a. So psi dash as such is not what you can say continuous at x equal to a by 2. So this is one thing. Now, let us move a little bit ahead. Okay, now what is the problem with the continuity of derivatives? See, why I'm emphasizing this concept? This is because of this, precisely this reason. You remember from your from your 12th standard calculus also, that if I want to write the derivative, second derivative, what it is equals to the derivative of the first derivative, right? Now, if your first derivative is discontinuous at a point, okay, so if your derivative is discontinuous at a point, let's say locally at a point, then how would you define the second order derivative? Because your first order derivative itself is discontinuous. Okay, so first order derivative is discontinuous, and you know from your childhood classes on calculus that if a function is non-discontinuous, it will be non-differentiable at that particular point, and if it is non-differentiable at that particular point, how would the second order derivative be defined? To rescue it, we have a function called as the Dirac delta function. Okay, that we're going to see in the next particular. How even if you've taken some classes on Dirac delta function, we've also derived this particular thing, that if we want to differentiate the unit step function, this turns out to be equals to Dirac delta function. Even if you don't remember, I'm just giving you a hint. This is one, you already know what is the unit step function. Unit step function is simply if x is less than 0, then the function is 0, and if x is greater than 0, then function attains a height 1. So clearly at x equal to 0, you have a jump discontinuity of quantum 1. So basically magnitude 1, so there is a jump discontinuity of magnitude 1 here at x equal to 0. This is the unit step function, and the derivative we define, the derivative we don't get very, the classically you cannot define the derivative, but in the distribution sense, the derivative turns out to be equal to Dirac delta function. This we have derived in our Dirac delta function classes using integral by parts. So I hope you will see that lecture, but I'm just giving you a hint that even if there is a discontinuity, not in the very classical sense, we can define the second order derivative here, but we can circumvent this problem by introducing the concept of the Dirac delta function. We'll see all these things later on. I'm just motivating you as to why I'm so interested in this particular problem. Okay. So as usual, let us first try to formulate this the way we formulate a quantum mechanical problem. So we are given a particle in the infinite deep square well potential with an initial wave function. I'm again writing with an initial wave function is equals to ax, and x lies between 0 and a by 2, and if it is equals to a times small a minus x, if x lies between a by 2 to a. Okay, now the first thing that really comes to mind is to solve this particular a. So first let us find this particular a, that let us find the normalization constant. So let us first find the normalization constant. So what would normalization constant be? So it's simply we have to integrate it psi star psi and psi star psi dx integral from 0 to a, it should give us 1, and which is equals to what? It is equals to 0 to a by 2. Our definition is simply ax. So it would be equivalent to writing a square x square dx. And then we'll have integral again, some a square would turn up here, and a by 2 to a. And we have a minus x whole square integration dx. Okay, integral. Okay, so if I want to really find what would be this, I think this is quite easy to see that it will be equals to a square. This would be x cubed by 3. And if I replace this a by 2, it would be a cubed by 8. Right? Okay, and by 3 would also come, sorry. And here also it would be a square by 3, but a negative sign would accompany here. Negative sign would accompany because a minus x is written. But understand, if I place initial condition a here, upper the upper limit, it will give me 0. So, and the lower limit again comes with a negative sign. So negative, negative, positive, again it will come out as a cubed by 8. So all this, when I summarize, I will get that a is equals to 2 times root 3 divided by a raised to power 3 by 2. This I'm leaving up to you to calculate. Okay. Now this is some equals to 1. All these things you can calculate on your own. So it will give me 2 times, so this is 12. 12 goes there. And all other things you can do. A cube goes down, and root over 12 is 2 root 3 only. Okay. So this is fine. Now the next, I have already told that if psi x is given in this form, the idea, we know that psi x forms a complete set. We already know that the psi x, the eigenfunction corresponding to the infinite deep square well, this particular eigenfunction psi x forms a complete set. And I know what I have already taught by complete set. What do you mean? By complete set, I mean that psi x can be expressed as linear combination of the eigengets. Okay. Now, in order to know this psi n, what was the trick? The trick was to multiply on both sides by phi n star and then integrate. And I know that this integral would come non-vanishing only if here, for example, I've written this integral would come non-vanishing only if n is equals to k. And so ck will be equals to nothing but integral phi k star psi x dx. So this is how you do. This particular trick I've already taught you a lot many times. And this particular trick you'll also find in most of the special functions also. Let's say in Fourier series you'll find, even in Legendre's polynomial also, because you know that the Legendre's polynomial of also form a complete set. Okay, so this. So if you want to find Cn, so how would you find Cn? Because I have already given that psi x can be written as summation n equals to 1 to infinite Cn phi n. And I want to find Cn. How would I find Cn? So what I'll do, I'll multiply on both ends with phi k star, and then, so let's say I'll multiply on both ends by phi k star psi x, and here I'll get summation n equals to 1 to infinity Cn phi k star and again phi n. So from here itself, it is quite evident. If I integrate it from 0 to a, and if I integrate this up from 0 to a, I know this will give me a non-vanishing answer only if n is equal to k. So Cn is simply integration from 0 to a. And what is phi k star or phi n star? If n is equal to k, I can also interchangeably use n instead of k. So it is equals to root over 2 upon a sine of n pi x upon a into what is psi x right now? So psi x is, okay, psi x is divided into two parts again. So we'll see that, don't worry. So Cn would be equals to what? It will be equals to root 2 upon a from 0 to a by 2. Our a was root over 12 upon a raised to power 3 by 2. And then we had some x also, ax. And then this will be sine of n pi x upon a. Then again plus root 2 by a. And then this will be again this particular fellow would come root over 12 upon a raised to power 3 by 2. Sorry. Okay, so this will be root over 12 divided by a raised to power 3 by 2 and integral from 0, sorry, a by 2 to a now, a by 2 to a. What this integration would be? Here you will get a minus x into sine of n pi x upon a and then okay, so this is how you will find your Cn. So again, in order to find the Cn, you will have to integrate it by parts. And let us try to do this. I mean, this is a log integral. So I'll say this as I1. I'll say this as I2. So I'll find I1, I2 separately and utilize the values here. Okay. So what would be I1? So let us find first I1. So we'll do, this is the differentiable function. This is integrable function. So in the first x sine n pi x upon a from 0 to a by 2 minus integral x derivative is 1, sine integral is cos and negative of that also. And again cos integration is sine. So I'm directly writing it so that we'll get this as equal to a square upon n pi whole square sine n pi x upon a. Okay, this is a. And from where to where? From 0 to a by 2. I hope it is clear till now. See what I've done. I mean, integral by parts. Okay, so integration by parts. First, I'm sorry. Here it will be cos. My bad. It will be cos here, I think. And since I've integrated, I'll also get a upon it. Okay. So if I integrate sine, I'll get ax upon n cos of n pi x upon a and a negative sign. Okay, I hope it is clear now. So I1, I would simply get if I place a by 2 here, because if I place 0, this is 0, fine. But if I place a by 2, I will get minus of a square upon 2n pi. And what is cos if I place a by 2 here? So a cancels. So I'll simply get cos of n pi upon 2. Okay, this is what I'm going to get. I hope it is clear till now, the first integration. Okay, so if I place a by 2 here, a by 2 cancels, a cancels a and it is 9. If I place a here, a by 2 again here, so I will get a square upon n square pi square sine of n pi upon 2. And if I place 0, it will be 0. So simply I1 is fine. What about I2? So I'll write it here only so that we'll not have to use much space. And coefficient, like both the constants here and constants here are the same. So no need to worry. I can take them on any day. Like both of them, I can take common out. So what would be I2? I'm doing it directly. I2 would be what? It would be equals to a minus x, and sign integration is simply a upon n pi cos n pi x upon a. From where to where? From 0 to a by 2. I would write from a by 2 to 0 because there is a negative sign. I have reversed it now. Okay, and now if I take another the second integral, now we have to be aware that this integration, this derivative would give me a minus. So minus minus becomes plus, and again this integral will give me again a minus. So it will become again minus. So after all, it will be like this. I think this will be minus a upon 9 pi, n pi, sorry, whole square cos of n pi x upon a. And this goes from uh, a by 2 to a. Here also it goes from a by 2 to, sorry, I think it's a to a by 2. Sorry. This is the second now. Second. So okay. So when I was reversing the limit, I made a mistake here. So you have to take care of that mistake. So this will go from instead of a by 2 to a, it will go from a to a by 2. And this integration goes from a by 2 to a. Okay, the second integral. I mean, the second in the by parts integration. So you have to differentiate this. A minus x when differentiated gives you -1. Sine n pi x upon a when integral gives you minus a upon n pi cos n pi x upon a. And again, integration of cos will give you a upon n pi whole square. So one negative would come from here. One negative would come from the derivative. And one negative already resides outside because of the integral by parts formula. Now I will write I2 equals what? If I place a by 2 here, so a minus a by 2 simply gives me a by 2 here. And here you have a upon n pi. And here you get cos of n pi upon 2. Okay, you get a cos of n pi upon 2. Plus, sorry, minus. If I write a here, a gives me 0. So don't worry about it. If I now write a here, so it will give me a upon n pi whole square. And this will give me cos of n pi. And again a negative, and negative is already residing outside. So plus a upon n pi whole square. And if I place a by 2 here, so I'll get cos of n pi upon. Okay. Now all this integral, so total integration that was Cn comes out to be equal to root over 2 upon a, root over 12 upon a cube, and this I1 plus I2. So I1 was minus a square upon 2n pi cos n pi upon 2 plus a square upon n square pi square sine of n pi upon 2. I think there again I made a mistake. So when I integrated it, cos gives me sine gives me cos, and cos again integration will give me sine. Sorry, sine here. My mistake again. So all these things are very difficult to do online. Okay, so here I'll get a sine. Sorry. Okay, and if I place a here, it will give me sine n pi, which certainly is 0. So don't need, I will not bother about this. And I think this is not cos, this is sine. Okay. Okay, so overall, I've got what a square upon n square pi square sine n pi by 2 plus, again this is a square upon 2n pi cos n pi by 2, and then again this is a square upon n square pi square sine of n pi upon 2. So this cancels out, and what is remaining? Simply Cn. And what is Cn? Cn is simply 2 into 12, this is 24. 24 gives me 4 into, oh, okay, so this is 4 into 6, this is 2 root 6 now. And these gives me again 2. So 4 root 6 upon a raised to power 3 by 2. And simply I'll get a square upon n square pi square sine of n pi upon. Now we have to think about what sine of n pi upon 2 can give us. It is a little elaborate problem, but so your Cn is equals to 4 root over 6 a square, and this is a. So this will give me a square is here, and a raised to power 3 by 2 is here. Okay, so this is one portion that I need to see. Just give me a minute. I have written it wrong somewhere. Okay, this root 2 by a also I forgot. So again, one root a also would come. Root a and a raised to power 3 by 2. This a square cancels out. So you get only 4 root 6. This is not 16. This is 4 root 6 divided by n pi whole square. Okay, and sine n pi by 2. Now, how you can write sine n pi by 2? See, if n is an even integer, if n is even integer, let's say 2, 4, 6, 8, then it will give me sine pi, 2 pi, 3 pi, so on and so forth, and I'll get 0. So if n is even, I'm definitely going to get 0. Now, if n is odd, then we really need to see. See, if n is odd, let's say 1, then we'll get sine pi by 2, which is simply 1. If n is 3, then we'll get sine 3 pi by 2, which is what? Which is minus 1. If n is 5, then we'll get sine 5 pi by 2, which is again 1. So we need to see how will I write this. But so this I'm writing minus 1 raised to power. If n is equal to 1, I want simply 1. So what I'll write? I'll simply write n minus 1. And then I divide it by 2. Now you see. So I'm writing sine n pi upon 2. Sine n pi upon 2 is simply minus 1 raised to power n minus 1 upon 2. I'm just verifying it for you. Place n equals to 1. So 1 minus 1 is 0. Minus 1 raised to power 0 is 1. So sine pi by 2 is 1. Place n equal to 3. 3 minus 1 is 2. 2 divided by 2 is 1 minus 1. So clear. Place n equals to 5. 5 minus 1 is 4. 4 divided by 2 is 2. 2 minus 1 raised to power 2 is 1. So basically sine n pi by 2 is this. And remaining this portion would come, which is simply 4 root over 6 divided by n pi upon 2 whole square. When n is odd. Okay. This sums up our problems. Basically now psi x you can represent in terms of your eigengets, and this will be this form: 4 root over 6 divided by pi square. Then you can place n belongs to what? Summation, and then root 2 by a, and then you will have Cn. Cn I've already written, but only 1 upon n square was remaining to be written. And then I can write phi n here. Instead of phi n, I'll write root 2 by a sine of n pi x upon a. And root 2 by a is simply constant, so I have multiplied here root 2 by a. Okay. And if somebody asks me at any later time t, what would be the wave function? Then wave function would be this entire thing, that is 4 root 6. I mean, this is a little lengthy problem, but what I want to convey from this still very far. Okay. So n belongs to odd. And here I'll get 1 upon n square. Oh, I forgot to write minus 1 raised to power n minus 1 upon 4. So this will be minus. This is minus 1 raised to power n minus 1 upon 2 and upon n square. And then I have the sign of n pi x upon a. And then e raised to power minus iota e n t upon h square. And I hope you don't want me to express this en. En, you know, it is equals to n square pi square h ket square upon twice ma square. So if I place it here, it will become a very massive structure. So I'm not doing that. So this is how your wave function would look like after some later time t. I hope it is quite evident now and it's quite clear. Okay, so this is how you do these problems. I'm doing it slowly because there are a lot many things to do, and doing it online makes it very cumbersome, and I have lack of space. Otherwise, these are not that difficult questions. You can do it on your own also. Okay, now as anticipated, uh, the wave function form looks like this. Okay, the initial wave function that was given to us was this way, and if I see my ground state of for an infinite deep square well, it comes out in this fashion. So barring this spike here, almost the trend is similar. So it tempts us to really find the probability of finding the particle in the ground state, or probability that we get a measurement, probability that an energy measurement, probability that an energy measurement yields the value even. It would be what? It would be equal to C1 mod whole square. And what is C1 mod whole square? So what would be C1? So just think about it. Cn I have already find. What would be C1? So I place 1 here. I place 1 here. It is 4 root 6 divided by pi square ka whole square. So C1 square would be 4 root 6 divided by pi square and whole square. And what it will give me? It will give me 96 divided by pi raised to power 4. And what is 96 divided by pi raised to power 4? Just calculate. And you'll find that it is almost equal to 0.9855 only. Okay. So again, you can see that the most contribution in the wave function, the most dominant factor in the wave function comes from the ground state. So again, you see how much close are we uh, from our anticipation. Okay. What would be the average value of energy? So average value of energy would be simply Cn mod whole square into En. And what is Cn mod whole square? Cn mod whole square would give me 96 upon pi raised to power 4, 1 upon n square whole square. So it will give me 1 upon n raised to power 4. And what is En? En is n square pi square h ket square upon twice ma square, and this all summed up. But n belongs to odd only. And so, okay, what is summation 1 upon n square? This is zeta 2, and this is equals this is equal to pi square upon 6. Okay. And if I take the odd values, if I'm taking up odd values only, this will come out as equal to pi square upon 8. Okay. This I can deliberate on any later day, but right now I'm not giving. I'm giving you as a homework. Let's say you just try to find. If I have already supplied you 1 upon n square, which is equals to pi square over 6, just try to find me the 1 upon n square, where n belongs to odd. This will come out uh, as pi square over 8. This is very easy mathematics you can do. If you are unable to do, kindly let me know. I'll do it for you. Okay. So this will be 96 pi raised to power 4. So this will be pi square here. N square cancel. So this will give me h cat square upon twice ma square outside. And this sums n belongs to odd 1 upon n square. Okay, let me try to do it. I mean, this is very easy to do. So I'm not doing it. So 48 here, 48 h cat square upon ma square, and this pi square and this pi square cancel. So you'll get 1 upon 8, and it is almost equivalent to what? It is equals to what? 6 h cat square upon ma square. And if you remember, your ground state energy was what? Your ground state energy was simply pi square h cat square upon twice ma square. And if you approximate your pi even as 3, so this is 3 square. So it is around 4.5. So this particular value would be around 4.5 to 5 h cat square upon ma square, because pi lies between what? Pi lies between 3 and 4 only. So this value would be between somewhere between 16 upon 8. So this is somewhere close to ground state energy only. Somewhere close to. You can find that it's not very far away from the ground state energy. Again, you can note if it is clearly evident that the ground state energy forms the dominant portion for this particular problem, where wave function initially supplied to us was this. Psi x was ax, a minus x. And with now see, very cleverly what I have done, very cleverly, I have used a formula Cn mod whole square an. Now, if somebody asks me that why did I not choose to use this formula? Why did I choose not to use the formula, the classical formula, okay, the initial formula that we studied for finding the expectation value of the Hamiltonian, which is psi star h cat psi. Why did we not choose to do this particular, using this particular formula? This remains to be a question that I'm going to address. But before that, okay, I have given you as homework, but I know you won't be able to do it. So let me do it for you. Otherwise, you'll say that it has got some very rocket, it has got some rocket science. Other values we have to remember, but this value you don't need to remember. Pi square over 6, you should remember, because this can be derived from the Fourier series also. But again, doing all these things in exam will take a lot amount of your time. So I will not suggest to do all these things in exam, but remember this. So I know that 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square plus 1 upon 4 square dash dash dash. This all comes out to be equal to pi square upon 6. And I only want to calculate this 1 upon 3 square, 1 upon 5 square, so on and so forth. Okay. So what I will do, I will simply write it as 1 upon 2n minus 1 whole square plus and summation n equals to 1 to infinity, and remaining part is what? Summation 1 upon 2n whole square. Okay, clearly 2 square is what? After all, it is 1 upon 2n. If I place n equals to 1, this will be 1 upon 2 square. If I place n equal to 2, this will be 1 upon 4 square, so on and so forth. And here it is pi square upon 6. If I want to find what is this, so summation n equals to 1 to infinity, 1 upon 2n minus 1 whole square would be simply pi square upon 6 minus pi square upon pi square upon 24, I think. Right? See, this is 1 upon 4 now. So you can take this 2 outside. So this will be 1 upon 4 and 1 upon n square. So 1 upon 4 into 1 upon n square. So 1 upon 4 into summation 1 upon n square. This will be pi square upon 24. Take that pi square upon 24 that side and just take an LCM here of 24. You will get I think 24, this is 4, so 3 pi square upon 24, which is simply pi square upon it. So I hope this is clear. How does it comes equal to pi square upon it? Now again coming back to the central problem, that why did I not choose to use this particular formula? Okay, uh, so the answer lies in uh, the the context that I created. That if my derivative is discontinuous, then how would I be able to define the second order derivative classically? Okay, in the sense that we do in the calculus only. Okay, so we know that I'll write it here so that we'll be able to make some good notes out of this. So you already know that d psi upon dx is clearly discontinuous. Is clearly discontinuous at x equals to what? A by 2. So how will we able to, why will we be able to define the second order derivative? And why second order derivative is required? You know that second order derivative, you know that the potential Vx is 0 in infinite d square well. So your h cat is nothing but minus h cat square upon twice m del square, so del square, sorry, del square psi upon del x square. So in order to have the uh, proper definition of second order derivative, one needs to have the first order derivative continuous. Now this gives us a big problem. So therefore we resorted to the the formula that we derived. That is, in order to find the, in order to find what? In order to find the expectation value of h, I simply did this particular calculation, that is summation Cn mod whole square into En. One thing is quite clear, that we may expect discontinuities at the endpoints. Okay, so like our own infinite deep potential well, we have discontinuities at the endpoint. That is, the derivative is discontinuous at the endpoint. Now here the problem is that the derivative is discontinuous at a midpoint. Now this gives us a little bit difficulty, and one needs to really address this. Not in exam, but otherwise also you should know. I mean, this is something that I'm not recommending you to know for your exam, but you should know for your at least other way. Like if somebody asks this particular thing in your interview, or even as a physicist, this question should tempt you, or this particular question should come in your mind, that why did I not use this particular formula? So I've already taught a few things. One of them was Dirac delta function. I've taught that d theta upon dx is simply Dirac of x. So basically, if I'm defining a unit step function, then the derivative of unit step function can be written in terms of the Dirac delta function. So derivative of unit step function can be written in the form of Dirac delta function. Now we'll utilize this trick, and then we'll see how to do this particular problem. Okay, because you see, in the classical sense, you cannot define the second order derivative, because you know what your calculus allows. Calculus clearly states that if your first order derivative is discontinuous, you won't be able to define your second order derivative classically. But we can obviously define it in the sense of distribution. And in the sense of distribution, d theta upon dx is written as Dirac delta function, that is Dirac delta x. Okay. So now, okay. So now if I want to write my initial wave function at time, let's say time t equal to 0, not, I'll make it a little bit simple. Let me write it for time t equal to 0. So what would be time t equal to 0? Because you know that in uh, even if I multiply this e raised to power e to power minus iota e n t upon h cat, while calculating your this particular thing. Okay, I'll come to that also, so that you won't be confused. What is psi x at t equals to 0? So psi x at t equal to 0, I will have to go again on the way back. This is 2 root 3 upon e raised to power 3 by 2. So it is little boring, I think root 2 over a root over 12 upon a raised to power 3 by 2, and this was some x, if x lies between 0 and a by 2, and if x lies between what, a by 2 to a, it was equal to a minus x, right? So basically what has happened, if I take the derivative, so what will be the derivative? Psi dash would be simply, this particular fellow would come. So 2 to 24, 24 is 4 into 6. So this will be like it's 4 into 6. So 4 into 6. So it will come out as, have I made some mistakes in there? Achha, a is 2 root 3 upon a by 2. Sorry. So this I have already taken care of, I think. Okay, so this was already calculated to be equivalent to 2 root 3 upon a raised to power 3 by 2. Okay, so this was already calculated. Okay, now if I differentiate it on the left hand side, the derivative will be 2 root 3 upon a raised to power 3 by 2. It will be 1 if x lies between 0 and a by 2. And if x lies between a by 2 to a, then it will be minus 1. So if I want to express this particular thing, so clearly there is a jump at, what you can say, there is a jump of magnitude 2 at a by 2. So how would I write? I will write the derivative in terms of the unit step function, which is 2 root 3 upon a raised to power 3 by 2. This is constant. 2 root 3 upon a raised to power 3 by 2. This is constant. 1 minus. I want to give a jump of 2. So 2. And I know that the jump is at x equals to a by 2. So the unit step function x minus a by 2. Okay. So if x is greater than a by 2, so if x is greater than a by 2, you know now this particular thing. If you don't know, I'm writing it here so that. So unit step function is expressed this way. It is equals to 1 if x is greater than 0, and it is equal to 0 if x is less than 0. So instead now I'm saying theta x minus a by 2, it will be equals to what? It will be equals to 1 if x is greater than a by 2, and it will be equals to 0 if x is less than a by 2. Okay, so if x is greater than a by 2, this will be equals to 1. So 1 minus 2 is minus 1. So here it is. And if x is less than a by 2, this would be 0. 1 minus 0 is simply 1. So psi dash you know. Okay, psi dash you already know. Now, if I want to find the second order derivative at time t equal to 0, let us say, it will be 2 upon 2 root 3 upon a raised to power 3 by 2. I've already told that the derivative of this unit step function is Dirac delta function. So you'll get 2 here. So this will be 4. The negative would follow. And this will be Dirac of x minus of a by 2. I hope it is clear now. So the second order derivative can be expressed as minus 4 root 3 upon a raised to power 3 by 2 Dirac delta function at x is equal to a by 2. Now, if you want to find the expectation value of h now you can find, or expectation value of energy measurement, now you can find. Otherwise, you won't be able to find. Okay, now, even if you had some, what is h expectation value of this particular thing, that is h, or you can say the expectation value of energy, or you can say that the average value of energy measurements would be simply psi star h cap psi. And h cap is what? It is some function of, I mean, this is an operator, del square upon del x square. Some constant would be there. I'm not bothered about it. But the time factor, if I multiply here, then in psi star, this time factor will become e raised to power iota e and t upon h squared. And this cancels out. So therefore, even if I evaluate everything at time t equal to 0, then things won't change. So therefore, the expectation value of Hamiltonian, or the average value of the energy measurement, would be equal to what? Now let us find it in the way that we were supposed to find. I'm not going to use the formula, okay? I'm not going to use the formula summation Cn mod whole square En. I'm not going to use it. I'm going to do it traditionally. So traditionally, how we do 0 to A psi star minus h ket square upon twice m, and then we have del square psi upon del x square. And I know that del square psi upon del x square is what? This entire thing. So I'll write minus 4 root 3 upon a raised to power 3 by 2 Dirac delta at x equal to a by 2. And this psi star is what? I know my psi star is simply, okay, so I minus h ket square upon twice m goes out, and this minus minus will become plus. So you will have a 4 root 3 upon a raised to power 3 by 2 here. Integration from 0 to a, you're getting psi star Dirac delta and psi star as a function of x into Dirac delta function stationed at x equal to a by 2. Now from here it is quite clear, you'll get what? You'll get this 2 cancels 4. So you're going to get 2 root 3 h ket square upon m into a raised to power 3 by 2. And you know, from your filtering property of the Dirac delta function, if you remember, fx into Dirac x minus a dx, this particular thing, let's say we are integrating upon the entire space, then the answer is f of a. Here also, you know, from 0 to a by 2, 0 to a by 2 will come in certainly in between. So this value would be psi star at a by 2. And you know that psi is a real wave function. So psi star is simply psi at a by 2. And I already told you that psi is continuous at a by 2. Whether you take this definition or you take this definition, this is one and the same thing. So what is psi at a by 2? This will be equals to 2 root 3 upon a raised to power 3 by 2 into a by 2. So this is 2 root 3 upon a raised to power 3 by 2 into a by 2. And finally, you are going to get what? So I think this is quite clear. 2 root 3 into 2 root 3 is 4. 4 into 3 is 12. 12 divided by 2 is 6. H ket square will come in its place. This m will come on its place. A 3 by 2 is a square. Sorry, a cube. And sorry, I'll have to write it. So, okay, this refracted. Okay, so a raised to power 3 by 2, a raised to power 3 by 2 is a cube, and a is here, so you will get a square. So this is equals to 6 h ket square upon ma square, and this is what we were getting from modulus Cn summation modulus Cn square into En. So only one thing we need to pay attention to, that if I calculate it in a manner, in the very classical fashion, then I will have to use the definition of the Dirac delta function. Otherwise, I won't be able to get it. Therefore, I consider Dirac delta function to be the most fundamental aspect in dealing in theoretical physics. So you'll find this particular Dirac delta function construction every time, like in electromagnetic theory, in statistical mechanics, even again in quantum mechanics. You've seen one more example where I have demonstrated that Dirac delta function formulation is indispensable tool. You cannot explain a few things. Like wherever there are discontinuities, if you want to find the derivatives there, uh, it becomes literally very difficult for you to formulate from the calculus that you know from your standard project. That is not incorrect. I'm not saying that is incorrect. I'm trying to make a point that certain derivatives you can only make sense in the distribution way. Okay, so that is how things are. I hope it's clear till now. Okay, so this is what we were to do today. I hope there is no such difficulties. Tomorrow, that is, we'll have a concluding lecture on infinite deep square potential well, where we are going to do all sort of different problems. And again, in a theoretical way only, but we'll concentrate more on problem solving developing the problem solving approaches. From after this lecture, you can comfortably attempt all the questions that have been asked in TIFR, JEST, NET, and GATE, and even in IIT JAM. So I hope from now, after this lecture, that is tomorrow's lecture, I hope you are going to attempt the previous year problems and get success in most of them. If you have any doubt, kindly let me know.